Hello everyone and welcome back to the OpenGL 3D game tutorial series. In this sixth episode, we'll see how to create and use the matrix. In particular, we will see how to create and use different types of matrix in order to rotate, scale, translate, and in general to transform our rendered objects. As always, we will face three main parts: requirements, design, and implementation of all the necessary things to create and use the matrix. Let's start with the requirements. We need a C++ IDE. In this series, we use Visual Studio on Windows and Qt Creator on macOS and Linux. The target platforms are Windows, macOS, and Linux. The target graphics API is OpenGL, and last but not least, a bit of knowledge of C++ programming language is recommended. Now we can start the design part. What's the problem to solve today? We want to create and use the matrix in order to transform our quadrilateral. So as first thing, let's see what is a matrix. In mathematics, a matrix is a rectangular array composed of numbers arranged in rows and columns. It has a lot of use cases, among which there is the transformation of points. With transformation, we mean translation, rotation, and or scale of vertices, and can be accomplished by the usage of the so-called transformation matrices. A transformation matrix is a matrix composed by the same number of rows and columns, the so-called squared matrix. We can have a matrix with 3 rows and columns, usually used to make transformation in 2D space, and then we can have instead 4 rows and columns when we want to make transformation in 3D space. Another important topic to face is the order in which the elements inside a matrix should be placed. We can have a 4x4 row measure matrix, where the elements are placed as a list of vectors of 4 elements from top to bottom. In a 4x4 column measure matrix, instead, the elements are placed as a list of vectors of 4 elements from left to right. The choice of how to order the elements, either by row measure or column measure methods, is only a matter of convention. For our project, we will use the row measure convention. At this point, let's talk about the various types of transformation matrices. We have the identity matrix, that can be defined as the default matrix. It has a series of ones along its diagonal, and among its useful properties, we have the possibility to multiply it with any other matrix, and we will always obtain, as a result, the other matrix without any change. Then we have the translation matrix that allows us to translate, offset, displace our vertices from a specific point to another one in the space. In a row measure matrix, the translation vector is placed in the 4th row. Other transformation matrices are the rotation matrices. These matrices allow us to rotate our vertices around a specific axis. Indeed, we have a rotation matrix for each type of axis, one for the x, one for the y, and another one for the z axis. Last but not least, we have the scale matrix. This matrix allows us to stretch our vertices in many ways, through the so-called scale factors. The scale factors are placed along the diagonal of the matrix. All these types of transformation matrices can be combined, or better to say multiplied, all together in order to achieve multiple transformations at the same time. So let's see how to perform this operation. The multiplication between two matrices is a process that starts by taking the first row of the first matrix and the first column of the second matrix. Then we have to multiply the first element of the first row of the first matrix with the first element of the first column of the second matrix. Then we have to sum it with the multiplication between the second number of the first row of the first matrix with the second element of the first column of the second matrix. and so on. In this way, the result is placed in the cell indicated by the intersection between the row and the column currently involved in the multiplication. In this case, the cell at first row and first column. In the same way, we have to do this operation between the first row of the first matrix with the second column of the second matrix. And we have to place the result in the cell at first row and second column, and so on. In this way, let's return to the combination of multiple transformation matrices. We can, for example, combine translation and scale matrices to both translate and scale our points at the same time. But we have to be careful to the order in which these matrices are multiplied. If we don't respect a specific order, we will get bad and weird results. Generally, we should multiply the scale matrix with the final result of rotation matrix, and in the end, the resulting matrix should be multiplied with the translation matrix. The combination of these matrices is usually called word matrix. The meaning of word matrix will be explained in the next tutorials. If you have questions, doubts, or comments about this topic, don't hesitate to leave them in the comment section of this video or in the Discord server. The link to the Discord server is available in the video description. Also, if you find these tutorials helpful, please consider to support their development on Patreon. Every single contribution makes the difference, regardless the amount. Very well, we have gathered all the necessary information to start the implementation. Let's start by going to Math folder. And here let's create the OMAT4 header file. Then let's add the OMAT4 class. As first thing, let's declare the math attribute that is a 2 dimensions array with 4 rows and 4 columns. The next method to implement is the setIdentity. We can define it as a clear method where we clear the entire array and then we set a series of ones along the diagonal. Let's call it during the constructor. In such a way, we initialize our matrix directly as an identity matrix. At this point, we can start to implement our first transformation matrix, that is, the scale matrix. As we have seen in the introduction, a scale matrix is nothing more than a matrix with scale factors placed along the diagonal. So let's pass these scale factors, one for each axis, through a obejcts parameter, and let's place them along the diagonal. It's around the time to try this method, so let's go to OGame class. Here, let's start to substitute the attribute scale in the uniform data structure with an OMet4 attribute. Let's call this attribute word. Then let's go to the onUpdate method. And after the computation of scale, let's add an OMet4 local variable called word. Here let's try to define this matrix as a scale matrix with the setScale method. For now, let's use the same scale computed in the previous tutorial. Let's initialize the data variable with the word matrix. And we have nearly finished. The last thing to do is to go to the vertex shader file and, as we have done in the C++ part, let's substitute the scale attribute with a met4 attribute. In the end, in the main function, let's multiply the position with the word matrix. Take care of the order in which position and word attributes are multiplied. Since we are going to use a row measure matrix, it's the vector to be multiplied with the matrix and not vice versa. So let's see if it works. And it works. The result is the same one of the previous tutorial, but now we are using a matrix. So let's go ahead and let's implement a new method in OMet4 class called setTranslation. With this method, we should be able to create a translation matrix that allows us to translate the vertices of our object. As we have seen before, the translation data in a row measure matrix are placed in the fourth row. So far so good. Let's go to OGame class and let's create a translation matrix. To do that, let's create another OMet4 variable called temp. With this temporary matrix, we want to combine all together the various transformation matrices inside word matrix. But before to do that, we have to implement a method that allows us to multiply two matrices. So let's go to OMet4 class and let's implement the per equal operator. As we have seen in the introduction, the process of multiplication between two matrices starts by taking the first row of the first matrix and multiply each of its numbers with the numbers of the first column of the second matrix. At the end, all these multiplications must be summed all together. And this kind of operation must be done for all the elements of the matrix, that are 16 elements. Very well, let's go ahead and let's combine the scale and translation matrices inside word matrix. Before to try this out, let's go to the vertex shader and let's tell to the compiler to treat the matrices inside this buffer as row measure matrices. Let's see if it works. And it works. Let's slow it a little bit. At this point, the only transformation matrices remain to implement are the rotation matrices. Let's start by implementing the rotation along the x-axis. Remember that the rotation matrices shown in the image are always row measure matrices. Very well, let's try it in the OGame class. And let's multiply it between the scale and translation matrices. So far so good. In this moment our quadrilateral is rotating along the x-axis. As we have done with rotation metrics along x-axis, let's implement the rotation metrics along the y-axis. Let's see if it works. And it worked. Let's implement the last rotation metrics along the z-axis. Very well, all the rotation matrices seem to work fine. The last thing to do is to combine all these rotation matrices all together. By multiplying the rotation z with the rotation y, and in the end the resulting matrix with the rotation x. Let's see if it works. And it works. That's all for now, folks. Today we have seen how to create and use the transformation matrices. The next time we will see how to render our first 3D cube in OpenGL. I hope you enjoyed this video. See you soon. Thanks for watching.